Our next speaker is Mr. Shyamal Kishore. He is a senior PhD student at the Department of Mechanical, Industrial and Systems Engineering, University of Rhode Island. He is working with Professor A. Shukla. Mr. Shyamal Kishore, you may make your presentation.
Thank you, Professor. Can you hear me all right?
Yes, you have about 25 minutes.
Okay.
At the 20th minute, I'll give you a reminder.
All right, thank you. So thank you for the opportunity to present and thank you for the introduction. So as Professor Swanti mentioned, I'm the student of Professor Arun Shukla, and Professor Simha is known to my advisor, and it is my honor to present at the symposium which is organized in his honor. So first, on behalf of all the students at our lab, I would like to wish Professor Simha a very happy retired life. And with that note, I would like to introduce the topic of my talk. Today, I'm going to be talking about dynamic underwater implosion pressure pulse interactions with submerged plates. I'm sorry if I can just turn my video on. Yeah, so today I'm going to be talking about dynamic underwater implosion pressure pulse interactions with submerged plates. So what is implosion? Essentially, if anybody is familiar, they would know that it is a rapid dramatic collapse of shells under hydrostatic pressure. And since we are looking at underwater situations, there can be a very complex fluid structure interaction phenomena that can occur when there is another structure nearby. And implosion usually is accompanied with a very dynamic pressure wave that is released and can be damaging to a nearby structure. And that is why this problem is of interest to us. In this work, this is comprised of experimental and theoretical sections. So we do experiments to reveal some of the hidden physics behind the phenomena, which is not easy to visualize and also cannot be expected a priori. And we were able to establish in the study a theoretical model to predict some of the key quantities of interest in this problem. And they were all informed by experimental results. So I want to begin with showing a video of an implosion of an aluminum tube. And here this aluminum tube is speckled, black and white, to measure full field DIC. So in this aluminum tube, you will see that the central region starts to deform inwards, and that is the indication that the critical collapse pressure has reached, and the shell begins to deform uncontrollably, and drawing the water in with it. And then as the wall contact is reached, then the buckle starts to propagate along the axial direction. And I'll play the video right now. And the collapse pressure of this tube was about 3 megapascals, or about 300 meters of depth of water. And like you can see here, because this video is taken at 50,000 frames per second, it is hard to appreciate the speeds at which this process occurs. And here in the implosion, the buckling pressures, the buckling waves can reach velocities of 700 meters per second, or 2,500 kilometers per hour. And the associated fluid motion, when brought to rest, can really result in damaging pressure waves. And that is why this problem becomes challenging and hard to understand and predict. So what is the pressure pulse that I'm talking about? Here's a typical pressure plot of such a problem. So the underwater implosion pressure phenomena can be broken down into 4 phases. And the plot here on the y-axis, we are showing overpressure pulse in megapascals. And the 0 level of the overpressure pulse corresponds with the buckling pressure of the tube. And on the x-axis, we have time in milliseconds. So in phase A, the tube walls become unstable and start collapsing. And the dynamic pressure begins to become negative, which means that it indicates that the fluid motion has started. And the pressure wave is converted into kinetic energy. And then in phase B, we call this region the underpressure pulse because it is negative and corresponds to the process where the tube walls are completely now uncontrollably collapsing. And in phase C, the wall contact occurs. And sorry, you can see the wall contact occurring here. And that is accompanied with this small minor acoustic spike. And then as the wall begins to propagate, as the wall collapse begins to propagate along the length of the tube, we have a large, broad overpressure spike followed by a decay profile, which is based on the length of the tube and other such factors. So this overpressure spike, in addition with the underpressure pulse, can be extremely damaging to a structure surrounding next to it. Additionally, we would like to also apply some of the knowledge gained in this work to apply to problems such as interaction of shock waves underwater with structures such as ships. So here is an example of what I'm talking about. So here in the first figure here, in the first figure, this is a shock testing of USS Gerald R. Ford, which is an aircraft carrier, and and this was being tested for its response to a massive shock wave that has occurred at a distance. So you can imagine that this problem is of interest to the Navy. And another relevant example in the case of India is India's only loss of a battleship in war, which was INS Kukri off the coast of Diu in Gujarat in 1971 war. So here there were 194 casualties when a submarine torpedo hit the ship and causing the loss of the ship. So the shock waves can really, from underwater, can really cause damage to structures, and that's why we want to study the problem of dynamic pressure pulse interacting with structures. In terms of implosion, a very interesting accident occurred in Japan at the Super Kamiokande Neutrino Observatory. So here in this figure, you can see a huge array of borosilicate glass shells, which are used for neutrino observations. And one of these shells, which is made of glass, imploded under pressure and caused the implosion, cascading implosion of 7,000 nearby shells. So this highlights that the problem that when you have an implosion, there can be a cascading effect of shock waves propagating outwards, which can then implode, and structures can implode, and then further structures can get damaged based on the implosion of the secondary structures. So broadly, that is why implosion pressure waves can be important. And implodable structures are often kept in structures such as submarines or under deep sea conditions in pressure vessels. So we would like to study the behavior of the plates which are next to it when a dynamic pressure pulse interacts with this kind of a pressure wave. The objectives of this experimental study are to experimentally study the interaction of fluid structure interaction process with two plates of extreme aerial mass densities. So at one extreme is 2 kg per meter square, and the other extreme that we'll consider is 100 kg per meter square. And based on that, we want to develop a theoretical model, which is starting from G.I. Taylor's model, original model in 1950s, I think, which then is, we want to predict quantities such as reflected pressures. So reflected pressure is basically, you can imagine the structures imploding here, and there's a shock wave that is released outwards in this direction towards the plate. And here is this plate, which is speckled for DIC, digital image correlation, for full field DIC measurements. And it is being observed by these high-speed cameras, which capture the event in real time. And we also mount dynamic pressure sensors at various locations. So reflected pressure is basically the pressure that is seen on the plate on the side which is facing the dynamic pressure source, here the implodable. And then we also want to get a measure of transmitted pressure, which is the pressure which travels across onto the other side. So if you have a structure where there's water on the other side, you can have transmitted pressure, not just the primary implosion pressure pulse itself, but the transmitted pressure can go onto the other side, and that can cause a damaging effect on the structures. And also, we would like to study plate deflection. So to do this study, we run our experiments in a pressure vessel facility in our lab. Here we have a two schematic view of the pressure vessel that is used for this study. So the pressure vessel is about a 7 feet diameter tube, and the plate is mounted at the center along with the tube, which is seen here, with pressure transducers all around. And then we have high-speed cameras looking through acrylic windows. These acrylic windows are about 6-inch thick to survive the pressure of the pressure vessel. And then there's an inlet valve. There is an inlet valve which is used to let nitrogen gas in, pressurized nitrogen gas in, and pressurize the whole tank. So once the tank is pressurized, the water pressure raises, and then we reach the buckling pressure of the tube. Once it implodes, then you trigger a switch, which will then enable the capture of data on all of your systems here, including the high-speed cameras and the pressure measurements. So what happens in general in an FSI phenomenon like this? So a pressure wave is released here. It is called the incident pressure wave. that goes and interacts with this plate, and that can be seen with this black curve. And then we have a reflected pressure wave. Some of the pressure wave gets reflected based on the thickness of the plate, based on the density of the plate, and then some of it gets transmitted. So this assumption, that the assumption in the study that we're making is that the pressure wave released from an implosion pressure front or implodable structure is going to be of a spherical nature, although that is not truly the case. However, it helps us simplify the explanation of the phenomena a lot. So when the structure implodes, the plate itself gets drawn in with the under pressure pulse. As the fluid is moving towards the collapsing walls, the plate also gets drawn into the collapsing walls. And once the plate makes wall contact, the overpressure pulse is reached. Then there is a return or retraction of the plate deflection. However, in our study, we did not observe the retraction back to the same levels as the on the other side, and that can be understood basically with the sense that once the fluid is getting pushed towards the collapsing tube, there is a momentum of all the fluid surrounding the plate, so it's going to be hard to push back all of the mass of water that is attached to the plate and completely and swing it back like an oscillator on the other side. Here's an example of an experiment conducted. On the left side, we have this spectral plate with a sensor which is mounted for measuring the transmitter pressure. And then we are going to look at out of plane displacement contours. And on the right side, we have this a video of the tube that is collapsing. And there are also several sensors mounted here. So what you will see is that at the center, you will start seeing elliptical contours start to develop based on the profile of the implosion. So I'll play the video and you can see what is happening. So you can see that the wall collapses and is followed by the elliptical structure developing, and then that propagates outwards, and then usually and the boundary effects start to play a role. So what about the pressures themselves? So we look at three planes of interest. The first plane P1, which is right behind the tube itself at a distance of about 0.5 inches, and on plane P2 we mount other sensors which are measuring the sum of the incident and the reflected pressures, and on plane P3 we measure the transmitted pressures. So in the thick we have two plates that we consider. This is the case of 100 kg per meter square aerial mass density. So it's a thick steel plate of ½ inch thickness. And what we expect to see here is that we will have a large reflected pressure because the incident and because it is almost like a rigid body. So when a pressure wave hits a structure, a rigid structure, the pressure doubles. So that is what we will see, almost about doubling of the pressure on the plane P2. But on the plane P3, we will see that there is a small amount of transmitted pressure. So here are the plots of this example, and you can see on plane P1 we have a pressure profile, and we see an overpressure peak of about 4 megapascals, and under pressure peak of about minus 1 megapascals, and that doubles almost in plane P2 to about 7 megapascals and almost minus 2 megapascals. And there's a small amount of transmitted pressure, about 1 megapascal and about 0.5 megapascal. So this is what we were expecting based on the thickness of the plate. You'll expect a very small amount of pressure pulse transmitted on the other side. Now, what happens when we have a low aerial mass density case? For that, we consider the thin aluminum plate of about 32 thousandths of inch plate thickness, and aluminum has low density, so the aerial mass density reduces. And in this case, we will see that there's a very small, very negligible reflection, actual reflection. So what you'll actually see on plane P2 is basically the incident pressure itself, and on plane P3, almost all of the pressure gets transmitted, and that is seen with these plots here. So here's the incident pressure pulse. Here's the incident pressure pulse, and then the reflected pressure pulse is almost about the same height and profile, and the transmitted pressure is also about the same profile. And this is much in contrast with the other previous case. So how do we understand this theoretically? Foundation work was done by G.I. Taylor, who developed a single degree of freedom model in 1963. So what I will do, my theoretical modeling is done in 4 steps. So first I take G.I. Taylor's single degree of freedom model, to a generalized pressure wave, because G.I. Taylor's work was done for an exponential decaying shock wave. So I will generalize that for a pressure wave like this. And then G.I. Taylor's work also only includes air backing, which means that there's no water on the other side. So in step 2, I will have a water backing effect added to this first step. And the first step, I just call it for convenience as model 1. And step 2 is model 2 with the water backing. And then step 3, this is where I add a bit more difference from compared to G.I. Taylor's work. In this model, we incorporate plate bending, and this plate bending solution given by Snedden in 1946 for a Gaussian pressure distribution. So I use that solution provided by Snedden to apply and follow same steps followed by G.I. Taylor to come up with a model that can predict and give us relevant quantities. However, there's one more correction that I would like to make, and that is how we understand the fluid velocity. So in G.I. Taylor's model, we essentially assume an acoustic kind of a fluid velocity model. However, when we include Rankine-Hugoniot effects to describe the fluid velocity, there's this something called afterflow fluid velocity, which is not just the main pressure wave, but there's something that is following behind the pressure wave associated with large fluid motion, and that has an associated pressure. So that velocity has to be corrected for this afterflow fluid velocity. And this was proposed by Adams and Yenny in 1948 paper. So I combine these characteristics to develop the model 4, which is the best model provided in the paper. So first, to begin with application of Taylor's model, and Taylor's model here's a schematic. So we have a pressure wave that is going out, and we have to assume a uniform planar distribution in this case. And Taylor's model considers a finite plate, and uniform pressure distribution is only true strictly when the pressure waves are coming from a large distance. So when we have implosions occurring in close proximity, or a shock going or explosion going off in close proximity, this assumption is not strictly true. That is one of the limitations of Taylor's model. So what we do and what Taylor does is considers the fluid velocity as with this equation, which is pressure over rho times c, and that is a well-known acoustic formulation of the fluid velocity. And we consider an areal mass density of m, which is mass per unit area of the plate. So on this side of the plate, we have the pressure acting on the force acting on the plate is basically pi plus pr, which is incident plus reflected, times the area of the plate. And then on the other side, we have a pressure, which is a transmitted pressure. We have a pt times area. So the net force acting on the plate is going to be pi plus pr minus pt. So Taylor's model considers this as a single degree of freedom model with a spring, and the spring essentially is accounting for the finiteness of the plate. So if you can figure out through other means what is the frequency of the plate, then that frequency is given by mu, and we have an areal mass density of m with the force acting of pi plus pr minus pt. So Taylor's model essentially develops this kind of a system for the plate. One more thing here is that the equation of continuity that is considered at the plate, and this is something that I've done an extension of Taylor's model, that is that the velocity that is induced by the incident shock or the incident pressure minus the velocity that is induced by the reflected pressure should equal the plate velocity, and also should equal the velocity of the fluid that is induced by the transmitted pressure. So these are the 3 basic steps of the model, and this is the model 2. For the sake of time, I would only be discussing model 2 and model 4. In model 4, I take the solution provided by Snedden, who calculated the plate response in air to a Gaussian pressure distribution. And this Gaussian pressure distribution can be a generalized sort of a load distribution profile to any kind of a shock loading or ballistic loading or other or dynamic problems of such kind. And Snedden considers an infinite plate with plate bending stiffness. And the equation of motion transforms in this way. So we have the net force on this side, on the left side, the same as before. And then we have the inertia term. And plus we have this other term. We have gotten rid of the spring force, but we have added this plate bending term, which is b squared times del power 4 of w. So this is the solution that Snedden provides in air. So I have combined the solution provided by Sneddon for fluid domain and also incorporated the equation of continuity for this case. So what is the difference about in terms of the afterflow fluid velocity? So there are two parts of this fluid velocity. One is called the radiated flow flux, and basically that is the energy that is released outwards that is never returning back to the source of the implosion, and the flux is proportional to 1 over r squared. So if you take a sphere that is enclosing the source, which is of an area proportional to r squared, the energy is always constant at any radius, which means that the velocity is constant at any radius, which means that this is going outwards to infinity and not returning. Then there's a second term for a spherically emanating pressure wave called the afterflow flux, and the flux there is proportional to 1 over r cubed. So when you multiply this with r square area, then you get 1 over r dependence. So that 1 over r dependence is shown here, and this is how we calculate the velocity, and this is provided by Aarons and Yenny in the 1948 paper for a spherically emanating pressure wave. So this is a hysteresis effect.
Mr. Kishore, you have 5 more minutes.
All right, thank you. So now I go on to talk about the results of the model. So in the explanation presentation of the results, I will use two terms called front side pressure and then backside pressure. Front side pressure is basically the incident plus reflective pressure. Backside is a transmitted pressure. So in model 2 for thick plate, we see that on the first plot here, there's a dynamic pressure on the y-axis and time on the x-axis, and the black curve is the prediction by the model, and the red curve is the experimental data. So we can see that the model falls short of predicting the doubling of the pressure here, and also over predicts the transmitted pressure. Additionally, we can see a plate displacement. Here is the DIC, a plate displacement obtained by DIC, and we see a very small plate displacement, which is in association with the acoustic formulation of the fluid particle velocity. So these are the results of model 2. However, when we go to model for the thin plate case, we see that the model performs better, and that is because much of the inertia is removed from the plate itself. So the plate thickness doesn't really play much of a role, since the model doesn't incorporate this afterflow fluid velocity. And from model 4, the predictions are much better, and you can see here that the overpressure profile is predicted much better, and the transmitted pressure is predicted much better. And then also the plate deflection here is over predicted because we are assuming an infinite plate sort of assumption. So the plate displacement is definitely going to be larger than the actual experimental data, and as expected, we get good match also with respect to the thin plate case. So in conclusion, here are a few important conclusions of the study. So we have looked at a thin aluminum plate with low aerial mass density, and we see that it is almost permeable to the implosion pressure pulse. Almost all of the pressure is transmitted, and almost nothing is reflected. For the thicker steel plate case, this almost doubles the front face pressure compared to the incident pressure pulse, and we have a small amount of back face pressure. And model 4, which is based on Gaussian distribution of pressure, is doing much better than the single degree of freedom model proposed by Taylor. Also, the aerial mass density of the plate is a governing factor, as I've not explained fully in details because of lack of time. However, the aerial mass density is one of the most important factors in the determination of the front face and back face pressure profiles. And also, incorporation of the afterflow fluid velocity is really improved our modeling predictions, and I think it is necessary for prediction of such quantities when large explosions occur, or dynamic pressure pulses such as implosion pressure pulses occur near a plate structure. And so with that, I would like to acknowledge the ONR, the Office of Naval Research, for funding this work. And I would also like to acknowledge Professor Arun Shukla for guiding me, and my colleagues at my lab, DPML. And also my parents and my sister are watching this webcast for the first time. They're seeing me present. So I would also like to acknowledge them for their support to me. So thanks to everybody for listening. I'm open to any questions.
Thank you, Shyamal, for that wonderful talk. Audience, there's time for some interaction. If you have any questions, you can pose.
There are a couple of questions. There is one question. I'll just unmute the.
Sure.
Mr. Rishabh, you can speak up. Well, let me relay the question. His question is, why wasn't damping considered?
Hi, can you hear me?
Yeah. Hi.
Hi, Mr. Kishore. I
Hi,
wanted
how
to
you
ask you, when you created the model for that, why
Yeah.
didn't you consider damping in the model?
So we did consider damping in the model, and what happens is that the equation that comes out is actually really complicated to solve, and there is no analytical solution available for that kind of an equation when you include damping in it. So we were restricted to going with the model without damping, and it turns out that the predictions work very well even without damping. And in the case of fluid motion, where when you consider water, the damping effects are not as strong. And the kind of damping that occurs is basically from the added mass effect or the inertia. When the fluid moves, the acceleration of the plate itself can radiate some of the energy away from the system. So that is the kind of damping that occurs. So it's more of a fluid structure interaction form of damping rather than structural damping. So metals also are generally have low damping coefficients. So these are the few reasons why we did not consider damping.
Okay, thank you.
Thank you.
Yeah, Vignesh Kannan, you can go ahead with your question.
Sure, thank you. Hi, Shyamal. Thanks for the really nice talk.
Thank you.
I just have a question, a couple of questions. One about your loading conditions. You said you used a Gaussian for the loading on the plate.
Yeah.
And I'm assuming that comes about because you have a spherical wave, but didn't you say that at some point it becomes a plane wave already?
Yeah, so that is the previous model. That is a model based on G.I. Taylor.
Uh-huh.
So in G.I. Taylor's model, the assumption is of a plane wave because the explosion is assumed to occur at a far distance. However, in our case, we have a near field implosion. So that is why we develop a separate model which considers.
So you do not assume the spherical wave becoming a plane wave because of the distance.
Yeah, we do not assume that. We assume that this spherical wave is applied like a Gaussian pressure distribution, since there is a solution available by Snedden in air for the plate deflection in this case.
Okay, and just a little detail about the imaging that you did. Was there ever an issue with having to phase match the fluid refractive index with your window because of the lighting, or was that never an issue?
Yeah, this was an issue actually. So I am actually not the original author of that work. This is one of the foundation works done in our lab. We were in our lab with Professor Shukla. The lab was a pioneer in developing underwater DIC measurement techniques. So what they do is they were doing a calibration process where they did consider refraction, and they underwent several iterations of the study, and they finally came up with a paper which explains that in detail. So I can send you the link of that paper to explain this better.
Great, thank you very much.
Yeah.
One last quick question from Shri Krishna. Please go ahead.
Sir, actually that question was for Professor Tejas, so I'm sorry about that.
No worries.
If there are no further questions, thank you very much, Shyamal, for that wonderful talk. And I wish you all the best for your defense.
Thank you, sir. Thank you.
And I hope that when the time, and I hope when the time comes, you will consider our ISC mechanical engineering for a faculty position.
Absolutely, Professor. Thank you. Thank you for the opportunity to give the talk, and my best wishes to Professor Simha from our lab students. And it was great to be presenting. Thank you.
Okay, thank you.